Record. Now I'm recording. So your voices are on here. Yay. Okay. So I've done a video lesson for day 6 McLaren series, day 7 Taylor series. And hopefully y'all worked on the review a little bit. So you've done these top 3 days. All right, down here, I've made a few edits in the 9B unit. A few edits here. Okay, so, all right. It's still in the same order that I had it before. Okay, so it's still in the same order that I taught last year. Like you'll see, integral test is where we were supposed to start. Then comparison test was the next day. Then alternating series was the day after that. Absolutely, I mean, this is the same order, but notice I put optional beside the ones that we no longer need. Okay, so like they took out integral test. Okay, they took out comparison test. So those are my first 2 days. They took out all the way at the bottom here, the Lagrange test. And so that's out. Okay, the only 2 days that I have on here that are mandatory, that are like content-wise, are alternating series, this 3rd day, which is where we're starting, and day 2, which is going to be tomorrow's thing. Okay, so, and I also put down the review, as I didn't make it mandatory, but that's going to be another day for us. But does that make sense? Is there any questions on like how I edited this right here? Any issues with that? All right. Now, okay, so like I said, okay, we've really got 3 things left to learn, and they're in these 2 days right here, alternating series and absolute convergence and ratio test. In this day 2 here, comparison test, there is one slide that is the P-series slide that I threw in there. And the reason that the P-series is in this day is because it's used with the comparison test, okay? So on today's notes, I'm doing alternating series, okay? I'm doing all of alternating series with one slide, the first slide, one slide from the comparison test, okay? So for those that printed off today's notes for alternating series, this is your first slide right here, all right, the alternating series. But I'm gonna start with this one slide from day 2, okay? And you can write this down separately if you want, like on a separate sheet of paper, or you can go back and look at it later, but I just wanna go ahead and clarify what P-series are. They're not gonna be the biggest deal in the world since we're not doing comparison test. But it's, I mean, I guess these might be the types of questions you might see, because I cannot imagine what other question they would ask with P-series without using comparison test. So, but anyway, let's go ahead and start with this slide, and then we'll jump into today's notes. All right, we good? Any questions? No? Good. Look at y'all being awesome. All right.
Quick question.
There you go. All right, what's up?
So on Canvas, it says that there's a Forbes video lesson under the optional ones. Are you going to be making video lessons for those, or
yes.
are those just kind of like there?
Great question, Nathan. So I'm making, so day 1 and day 2 here, and day 3, those are going to go in order: Monday, Tuesday, Wednesday. But on Wednesday, I'm going to start making videos for these optional dates, so you can have them if you want to go back and watch them. Okay, so I'm probably going to make these over the spans of Wednesday through Friday, and y'all can watch those as you like. They're not going to be mandatory at all, but I just don't want to like jip you from all of Calc 2 in case you want to move on to Calc 3. Make sense? We good?
Yeah, I got that.
Yeah, what's up?
Like, so how will AP review work now? Like, will you just pretty much take out the stuff we don't need to know?
Yeah, pretty much. So my plan is to spend this whole week making sure that you get the remainder of the content, and maybe do some optional stuff if you want. I don't know. This whole week is my goal is for it to be just doing Unit 9B and reviewing that. Then starting next Monday, I'm going to start with my usual review. So I'm going to try to go back to AB a little bit, do some review, and kind of build up to where we're at. And you're right, I'm just going to cut off the units that we don't need. I got like about 5 days worth of AP response topics that you probably need to write and to memorize, like the ones that pop up the most. I'll probably cut down to 4 days now with the content being cut. But then we'll just do a bunch of practice. So yeah. And once I get updates about how grading works, I will share that and how we can get some daily grades or something to help us. But as of right now, I got nothing. So
what about the project, the manual?
Oh, the project after the AP exam?
So the manual.
Or the manual.
Oh, the manual is going to be definitely a grade. I wouldn't worry about a due date just yet. That'll probably be towards the end of the semester.
What about those
Yeah.
optional topics? Are there any of those optional topics on the?
I will update the list up at the top here. So if you go to the top, I will update the manual for us with the topics. I won't make those topics required, so I'll take that off of the manual and update a new list. I'll do that after the lesson.
Bro,
Oh, okay.
optional topic should be a extra credit. Hear me out.
No. All right. Any other questions before we move on? We good?
Oh, so we have like tests and quizzes in here. Okay, can you do that?
I don't know yet. I gotta wait and see how the online structure is gonna work. And did y'all get that message from Dr. Louder about picking up computers if you need it or whatever? So that means we're kind of pushing towards online study, and they have not given us any guidelines about grading with that yet. So I will just let you know as soon as I find out. Anything else? All right. Well, stop me if you have questions throughout. I'm gonna try to just kind of whiz through this a little bit. And anyway, all right. P-series is used for comparison tests, and you'll kind of see why. It's because P-series are very easy to identify if they converge or not. And so if I'm trying to compare that to a more complicated function, and we know how the comparison test works, having a P-series to compare to makes it a lot easier to use. So a P-series is in this form. So it's the summation n equals 1 to infinity of 1 over n to the p power. Okay, so like if you were to expand it, it's going to be 1 over 1 to the p power plus 1 over 2 to the p power plus 1 over 3. P is just a constant, so like it could like 1 over n cubed is a P-series. 1 over n to the 4th is a P-series. So, and we've talked about P-series a little bit. The most famous one is the harmonic one, right? So like the summation n equals 1 to infinity of 1 over n. All right, that's our harmonic series. We talked about the harmonic series a little bit. We showed a proof about how it diverges, okay? And that's when the P-series has a p-value of, oops, that should be a 1, of 1. And it's at that point where it shifts from convergent to divergent. So with P-series, I get this, I guess theorem, this formula. It says the P-series, the summation n equals 1 to infinity of 1 over n to the p, is convergent, okay, if p is greater than 1. So like 1 over n squared is convergent. 1 over n cubed is convergent. We talked about this, like the textbook said, it's because, what, are other people doing that? Can y'all write on this?
Yeah, no, you can totally write on this. There's if you have it on mobile, there's a pen that lets you just draw. That's crazy.
Okay, don't do that.
That is crazy.
Don't do that. Anyway, so the textbook said that like anything with a p-value like greater than 1, those are like increasing at a fast enough rate that they are able to have an infinite sum. So the textbook's explanation was kind of crappy, but so just basically know that if it's greater than 1, it converges, and if it's less than or equal to 1, so like 1 over n to the 1/2 power, then that would be divergent. Okay, so that's super. Delaney, yes, you raised your hand.
What does the harmonic series thing say? It's 1 over n times what?
Sorry, 1 over n to the 1st power. That's to the 1st power.
Okay.
Yeah, or just 1 over n. So I can even erase that. 1 over n. Oops. Okay. So that's the harmonic series. So again, like these are super easy to identify if they converge or diverge, and that's why they're used for the comparison test, because I can compare it to something that I know 100% converges or diverges, and that'll be in a later video lesson. But like for instance, like okay, which of these converge? Well, if you look, I mean, this is like in A, this is obviously a P series. P is equal to 2, which is greater than 1, so therefore it converges. It's that simple. So if you have it in the form 1 over n to the p, it's that simple. Like down here, p is equal to what? 1/2. And 1/2 is less than 1, therefore it diverges. That makes sense. All right. Again, like in order to do the p-series and identify convergence or divergence, it's got to be 1 over n to some power, which if you notice in C, it's not quite like that. So I'm going to take the 3/2 out because it's just a constant. So this is like saying 3/2 summation n equals 1 to infinity of 1 over n cubed. And 1 over n cubed, p is greater than 1, so therefore it converges. All right. Any questions there? I wish there was a way I could like scroll down. Someone wrote big 4 at the top of the screen. That's great. It's good. This is going to be fun. I can tell.
Big 4.
Anyway, let's see. I wish there was a. How can I slide down? Is there anything to slide down? It's going to drive me crazy. Oh well, I'll just squeeze it in there. Okay, so like the last one here, notice how it's like a sum of 2 different functions. Like this is like a kind of a point where you're supposed to recognize, okay, this first one, well, that's a p-series. Okay. And this one right here, 1 over 8 to the n, you're supposed to be able to recognize, oh, okay, 1 over, so n is in the power. You're supposed to recognize that's just geometric. Okay. So we know how to discuss the convergent and divergence of a p-series, and we know how to do the convergence and divergence of a geometric series. So we can split that into 2 series. I can say the summation n equals 1 to infinity of 1 over n cubed. And I can talk about the summation n equals 1 to infinity of 1 over 8 to the n. Okay. Oops, I forgot the cube right here. So I know with the p-series that p right here is greater than 1. So therefore it converges. Okay. And 1 over 8 to the n is the same thing as 1/8 to the n power, okay? Because like 1 to the n and 8 to the n is the same thing, so I can take the n power out. And I know that this rate right here is less than 1 as well. Okay, the rate, which is 1/8, is less than 1, so therefore it converges. So that's going back to our geometric lesson. So, it was a mess me trying to squeeze that in there, but does that make sense? So being able to do p-series and then being able to do geometric. It's that simple. So questions, comments, concerns on p-series. All right, that was the first slide on the comparison day, so that you'll see that completed on there. But I'm gonna go ahead and jump into the next stuff, which is alternating series. That stuff's still there. Thank you. Someone delete it. Delete. There you go. I'm okay with big 4 up there, but there you go. All right. All right. So alternating series. So we know what alternating series is. This lesson is all about how to identify if an alternating series is convergent or divergent. So y'all are pretty lucky, I guess, in the sense that like the whole point of Unit 9B was to discuss types of tests for convergence and divergence. And all the stuff they cut out most of the hard stuff, most of the hard tests, which is good for y'all. But they left 2 tests for us to discuss, and that's alternating series today, tomorrow's ratio test. But I think you're going to like alternating series. So we know what alternating series looks like. We've seen it before. Either the even or the odd terms are negative. Terms are negative. And your ID here that you can easily tell if something's alternating is, remember, it's going to be -1 to some power, like n, or -1 to like the n -1, something like that, n + 1, I don't know. Okay. But remember that the sequence itself looks like this. It goes positive, negative, positive, negative, positive, negative. And the idea is hopefully that it's going to be converging to 0. And if the sum is converging, or if the sequence is converging to 0, then the sum is going to converge to some value. I don't know what that value is, but it's going to get closer and closer and closer to that value. All right. Now, there's a real easy way to tell if a alternating series converges or not. There's really only 2 steps, okay? The criteria, though, is that a sub n is greater than 0, okay? Whenever you're in the form summation n equals 1 to infinity, negative 1 to the n, so there's your alternating series part, times a sub n. Okay, so whenever you're in this form, 2 things you have to show to make sure an alternating series converges. The first one you already know. It's the test for divergence. That first test we talked about. You have to show that the limit as n approaches infinity of a sub n equals 0. So you have to show that this piece right here, as you go to infinity, is going to be approaching 0. Okay, so that's the test for divergence. And that's the first test for anything you do, really. So I don't even think that's really anything new. And then number 2, you have to show that the values of a sub n, so these terms a sub n, you have to show that they are getting closer and closer to 0, that they're decreasing. So you have to show that a sub n plus 1, that the next term is going to be less than the previous term for all of n, okay? And this part right here for all of n can be a little wishy-washy, and we'll talk about that as we get to it. But basically, it has to be ultimately decreasing. Okay, makes sense. Oh, and the reason I use the word ultimately is because sometimes, like at the very beginning, it may increase for just a second, but then ultimately, as you go on to infinity, it is decreasing. Okay. And we're gonna talk about how we show that in a second. So here's your 2 ways to do alternating. Questions on that? All right. The next few slides are just examples. So I think that's going to be pretty helpful for us just to be practicing examples. So pretty good start here. It says determine whether the alternating harmonic series is convergent or divergent. Okay, convergent or divergent. I like this one to start with. Because okay, first of all, this top part here, negative 1 to the n minus 1 power, that's my alternating series part. Okay, that is what my ID is. That's what tells me it's alternating series. Now the rest of the function that I didn't circle, that's my a sub n. Okay, so like a sub n in this case is going to be equal to 1 over n. Okay. So it is in the form, we got the alternating series times some a sub n. It's just 1 over n. Now it's kind of interesting though, because we know that the series 1 over n, we know that actually diverges. It's a harmonic series, or if you think of it as a p series, it's not greater than 1, so it diverges. But it's interesting about the alternating harmonic series. We'll see what kind of happens as we do that. Okay, so number 1, remember, we have to discuss the test for divergent. We have to say that the limit as n approaches infinity of my a sub n, so that's the piece without the alternating series part, we have to show that equals 0. And that does, right? I mean, that's you can talk about it in terms of like your end behavior rules or whatever, but that's obviously going to be reaching 0. Okay. But the other part that we have to show is that a sub n plus 1 is less than a sub n, so like it's decreasing. Okay. Now I know that the way that they like to see it on the AP exam to discuss that, if I want to show that a function is decreasing, what could I use? Decreasing, intervals of decreasing. We're going to talk about the derivative. Okay. So in order to show this, I'm going to discuss the sequence as a function. All right, instead of 1 over n, I'm going to discuss it as 1 over x. And I'm going to show that that function is ultimately decreasing as we go from 1 to infinity. Okay. So f prime of x, for instance, if you take the derivative of that, is just equal to negative 1 over x squared. Okay, and that's just doing power rule. You've done it a bunch of times. Okay. And so what makes this 0 and undefined is, well, at x equals 0. So we'll put that on my number line. Okay. And if I test, and I'm only going to test points to the right of it because it's going from 1 to infinity, so values are always positive. So if I plug in like, for instance, 1, 2, 3, 4, it's always going to be negative, meaning that my function is always decreasing. So that's the work you have to show. You just have to show. Therefore, by alternating series test, I've got to write the whole thing. Summation n equals 1 to infinity of -1 to the n minus 1 over n is convergent. All right. Easy enough? Any questions on that? Comments, concerns?
Wait, how did
Can
you
you wait
get,
a little bit so I can copy all this down?
Yeah, absolutely. I'll give it a second. What was your question, Lisa?
how'd you get a sub n plus 1? Which one was that?
Like right here?
Yeah.
So that's just a general notation that we have to prove. We have to show that the next term, which is a sub n plus 1, is going to be less than the previous term for all of n.
Oh, so you're just showing that it's like decreasing?
Yes, all this means, yeah, let me put that in parentheses. All this means is to show that it's decreasing. That's all we have to do. So that's a better way of saying it. So we have to show that the limit of a sub n is approaching 0, so the values are getting smaller and approaching 0. And we have to show that the sequence a sub n is always decreasing. If that's the case, then the alternate series will be convergent, which is
Why did you
interesting.
have to take the derivative?
Go ahead, what?
I said, why did you have to take the derivative though?
Oh, okay. So like, how do I prove this? How do I prove that it's always decreasing? Well, I could just say, well, it's obviously decreasing because anytime I increase n, it's becoming smaller and smaller. But you can't just say, obviously it's decreasing. You have to show it somehow. Well, how do we show something's decreasing? Anytime we talk about anything with decreasing or increasing, we can discuss the derivative. So that's the most, what's the word I'm looking for? That's the most appropriate or consistent way to show something's decreasing. Does that make sense?
So are you showing it for the sequence or the series?
I'm showing it for the sequence. I'm showing it for this part right here. So what we're doing is we're just looking at the a sub n. We're kind of ignoring the alternating series part. And if I can show that that a sub n is both approaching 0 and decreasing, then yeah, we're good to go. Then the alternating piece is convergent.
I have another question.
Yeah, what's up?
So if they give you like a harmonic series on the exam, can you just like say that it is a harmonic series, therefore it's divergent?
Yes,
Okay.
that is the ID from harmonic series. Absolutely, 100%. You can discuss it as a P series if you want. Say P is equal to 1, and therefore it's divergent. Yeah, P series are very easy to identify convergence or divergence. All right, let's do one more example with this, or I have a few more examples. See how we go. Okay, look. So it says determine whether the series blah, okay, is convergent or divergent. So like the whole point of this unit was I was going to give you a whole bunch of different types of series, and you had to identify what type of series it was in order to use a certain test. So we only are going to have 2 mandatory ones now, so that's good for y'all. But the idea was to recognize, oh, okay. Oh, I see. What are you doing now? I see this piece of it right here. -1 to the n. You see that instantly right off the bat, you're thinking, okay, that is an alternating series. Okay. And if it's alternating series, we have 2 tests, or I'm sorry, we have 2 criteria that we need to show to figure out if it's convergent or divergent. Okay. Number 1, all right, is we had to see if the limit as n approaches infinity of a sub n equals 0. Okay. Well, what is a sub n in this case? 3n over 4n minus 1. It's the piece of the function that's not the alternating series. Okay. So is this true? So we're going to say that the limit as n approaches infinity of 3n over 4n minus 1. Does that limit equal 0?
No.
No, what's it equal?
3/4.
3/4. Perfect. Okay, and that's just based off of our end behavior rules with rationals. I mean, you can notice that, hey, the power up here is 1, the power here is 1, so the limit, yeah, which does not equal 0. So therefore, the series diverges. Now, here's the part that's interesting with this, and I just want to make sure if this pops up on the final exam, you don't get it wrong. The series diverges not by the alternating series test, but by the test for divergence. Yeah, it's kind of weird. So like, I know you're starting off by doing step 1 of the alternating series test, but if step 1 doesn't work, technically what you did is you showed it was divergent by the test for divergence. So that's what you're supposed to say. You're not supposed to say by the alternating series, because this right here is the test for divergence. And this is the part that kind of frustrates me about what they took off. Like, they do not require you to know the test for divergence, but it is a part of the alternating series test, which is what they do expect you to know. So I don't know. I don't know why they do that.
So
Anyway.
for the alternating series test, is that if the two, like, if it passes the test, that means that it's convergent?
Yeah. If it passes both the tests, like steps 1 and step 2, if I can check both those off, then it's going to be convergent. Yeah.
So if it doesn't, then it's divergent?
Yes. So
Okay.
let's say that, like, for instance, like check, like step 1 is a check, okay, but then step 2 is an X. Then you would say, okay, well, the series diverges. Then you would say by the alternating series test, if it doesn't pass criteria number 2. Okay. Everybody had a chance to write that down? Anybody need me to hold on for a sec? All right, let's keep going. All right, test the following series for convergence or divergence. Okay, so I think this is pretty easy to tell that this piece of it right here, that's my alternating series piece, and the rest of it is my A sub n. So then I'm gonna do my test for alternating series by starting off with the limit. Okay, that's ugly. Erase that. Okay, so we're gonna do the limit. N approaches infinity of n squared over n cubed plus 1, which does equal 0. Can you agree on that? I mean, you got a higher power on bottom than you do on top, so that is obviously going to converge to 0. Okay, so
Mr. Forbes,
yes,
your volume is like kind of fading away sometimes, and it's like
I'll tell you
really hard to
exact.
hear.
Okay, all right, okay. As I'm talking right now, is it fading away right now?
No, it's fine. It's usually like when you start writing something.
I'm covering up something.
When you look away.
Yeah.
Is
Yeah,
it
it
like
gets a little
awful?
bit choppy.
Can you still hear it? Okay, you can hear it right now. All right, next time
we
that
can.
happens, like, yell at me, okay? So
Okay, note taken.
Don't
I
yell
think
too
you're
loud.
covering up the microphone when you start writing.
Okay. Well, thank you. Let me know if it happens again. So, all right, so we're good there. So then step 2, is it good? Very good. Step 2.
Step 2.
We need to do a sub n plus 1 to make sure that that is going to be less than a sub n. And how you want to do that is you want to discuss the a sub n as a function and discuss the derivative. So I'm going to say, all right, we're going to say f of x is equal to x squared over x cubed plus 1. And now let's take the derivative and find the intervals on which it's decreasing and decide if it's ultimately decreasing. Okay, so I guess I can do that over here to the right. Let's talk about f prime. F prime of x equal to. I guess the best way to do this one is probably low d high minus high d low. So I'm going to do low d high minus high. Low d high minus high d low all over low low. How's my volume?
Fine.
Okay, cool. Fine. All right, now we got to figure out when this is equal to 0, so or undefined. So I guess it's best to probably simplify the top a little bit. So, what was that going to be? 2x to the 4th plus 2x minus, is that 3x to the 4th? The top simplifies down to 2x minus x to the 4th over x cubed plus 1. All right. So at the bottom, what makes that 0? At the bottom, what makes that 0 is x equals -1. So there's one value. And the top, we'll do a little bit of math with that. I'll take out a GCF of like an x maybe. I got, oops. And I'm left with 1, or 2, sorry. 2 minus x cubed. Okay. And what makes that 0 is actually going to be x equals 0 and x equals, is that going to be the cube root of 2, I think? Okay. All right. So if I put that on my number line, okay, I'm going to put -1, I'll put 0, and I'm going to put cube root of 2. All right, here's the thing though, we're talking about a sub n is greater than 0, so we're starting off really at 1, if that makes sense, because that's where our series is starting. So really, I don't have to look anything before 0 or before 1. I'm just going to look at that interval. Okay, so the cube root of 2. Maybe if I plug in like 1 or something into this, or to see if it's positive or negative, it ends up being positive. Okay, you can test that if you want. It's going to be negative on top. Wait, 2 minus, yeah, it'll be positive on top and positive on bottom, which makes it positive. And if I plug anything greater than the cube root of 2, like 10 or something, it's going to end up being negative. Okay. All right, so the question is it like, is it ultimately decreasing? Yes. Okay. Now I realize right here it's increasing slightly, but once I pass this point, and that's like x equals 1 point something. So once I'm past that to like x equals 2, 3, 4, then it's ultimately decreasing. Okay. So I'm going to say right here, I'm going to say that it is ultimately decreasing. Okay. And it's going to be decreasing whenever n is greater than or equal to 2. Okay, if n is equal to 1, it's increasing, but like once I go past this point right here, the cube root of 2, which is like 1 point something, so I'm at like n is like 2 or 3 or 4, then it's going to be ultimately decreasing. So it takes only one term before it starts to decrease. That's what I mean by ultimately. Does that make sense? Then you would say, therefore, by alternating series test, decreasing. Or not decreasing, convergent.
Then why did you put n is greater than or equal to than 2?
Right there?
Yeah.
Whenever I was doing the derivative up here, do you notice how I changed it to a function? Okay, the reason I changed it to a function is because the function is continuous, so I can talk about its continuous intervals. And that's how I got this point down here at the bottom, the cube root of 2. Like I wouldn't have got the cube root of 2 if I was just considering it as a series, because cube root of 2 is not like an exact integer. And the cube root of 2 is like 1 point something, okay? So if I'm thinking about it as a series, that's between n equals 1 and n equals 2. Does that make sense? So at n equals 1, it's increasing, but at n equals 2, it starts to decrease. So ultimately, at n is greater than or equal to 2, it's going to be decreasing. Does that make sense?
Yeah, that makes sense.
I was just trying to like, all this part was just to let you know that, hey, it's definitely decreasing. It only took one term before that happened. Okay. All right, how do you feel so far? Any questions about alternating series test? Nothing too bad. All right, I got like, what, 3 more examples to try with that? 3 more? So And they're not too bad. They're all pretty similar. Oh, wrong way. There we go. Do I want to do this one? Yeah, I'll do this one. Yeah, okay, that's good. All right, so like this one right here, alternating series part, okay? So a sub n is equal to 1 over e to the n, right? So because it's alternating series, I can try those two tests. So I'm going to start off by saying, all right, let's do the test for divergent. Let's say the limit as n is approaching infinity of 1 over e to the n. Does that equal 0? Yeah, 100%. You got an exponential growth on bottom and nothing on top, so that's definitely going to reach 0. So that's a check. And then number 2, okay, we want to think about f of x as e to the, I'm going to go ahead and say e to the negative x. Is that okay with y'all? I just went ahead and changed it to 1 over e to the x and went ahead and brought that power to the top so I can go ahead and take an easy derivative. Okay, so I'm going to say f prime of x equals, what's the derivative of e to the negative x? Negative e to the negative x, right? Any questions on that? All right, derivative of e to the negative x is e to the negative x times negative 1. All right, is there anything that makes that 0? No. Okay, there's nothing I can plug into a power to make it equal to 0. But regardless of what I plug into the power, all right, it's always going to be just some positive number times negative 1. So on my interval from, I mean, if you want to start at 0, because we're dealing with positive values for n, you can. But no matter what value I plug in, it's always going to be negative. So that is a decreasing function. So this is a check. So therefore, by alternating series test, it is convergent.
Wait, so when you do the second part, what n value do you start at? Is it 0 or 1?
I always start off at 0. You can start off at 1 because that's technically the value that you're starting off with. But we never go back to negative numbers in series, so that's why I just started up at 0. That part doesn't really matter as much. Either 1 or 0 is fine. It will not affect your answer or getting credit for justification. Right? We like this, right? Not bad. Y'all are lucky. You got the easy tests. This is the easy test, I think. I don't know. Okie doke. 2 more in this. We'll be doing all right. Must be recording. I hope I am. All right.
Yeah, for a second there, your audio cut off.
Oh, okay. Is it good though right now?
Yeah, it's good now.
All right. Any
I
questions?
think
'Cause
your phone number.
You think what?
I think. Never mind. Just never mind. Ignore me.
All right, no worries. You're fine. All right, so like right here, alternating series part. So a sub n is equal to n over n plus 1. Okay. And y'all could probably already do this without me explaining it by now, but we'll just keep going. The limit n approaches infinity of n over n plus 1. What's that equal to? Not 0. So therefore, by test for divergence, the series, I'm not going to write the whole thing again, but the series diverges. And I knew that equaled 1 just by my end behavior rules for rationals. Okay, take the leading coefficient, equal to 1, not 0. All right. So take you a second and write that down.
So if we only have to do step 1, then we just write that it's not the alternate series. Step 2 is alternate series, right?
Yes, you write by test for divergence. It's no longer considered a alternating series test. Absolutely. Okay. Anything else with this? Any other questions? All right, one more with this, and then I'm gonna jump to one more new thing, and then we should be done. Okay, how am I doing on time? Doing okay. All right. So alternating series piece, I always circle it. You don't have to, but I always do. Alternating series, that way I know what my A sub n is. It's ln of n over n. So there's that. Okay. I like doing the first step for this one. If I do the test for divergent, I do the limit as n is approaching infinity. And I'm going to do ln of n over n. Okay, so ln of n over n, taking that limit, it's kind of weird. I wish we could have more of a discussion, but that's okay. Ln of n over n, like, okay, if I plug infinity into that, okay, it's ultimately going to come out to this right here. If I plug in infinity to ln, it's going to approach infinity. If I plug infinity in for n, it's going to be infinity. So how can I discuss this limit? What could I use? L'Hopital, right? Yeah, we got L'Hopital. We got infinity over infinity. If that's the like what you get to, then we can say, remember that you don't want to write it like I just did. You want to discuss the limit of the top and the limit of the bottom. But for sake of time, I'm not going to do that. I'm just going to say by L'Hopital. By L'Hopital. This is the same thing as saying the limits, if I can write nice, in, oh my God, that's so ugly. The limit is n approaches infinity. Okay, so the derivative of ln of n is 1 over n. The derivative of n is 1, or just simply 1 over n. And I know the limit of that equals 0. So that step's good. Okay.
That's called big brain hours.
Yeah, right. All right, now the next part, trying to figure out if a sub n plus 1 is indeed greater than a sub n. We're going to take.
You just faded out again.
Oh, am I good now?
Yeah, now you're good.
Can you just repeat what you said, like starting from like the next part?
Yeah, absolutely. And just keep doing that if I go out. That's fine.
I think what's happening is you're moving far away from your mic, so you might want to figure out where your mic is, and then.
I have no idea where my mic's at.
Talking to that. If you're using a laptop, there's usually like a hole in it. That's generally your mic.
Probably right next to your camera.
Yeah, that or like somewhere.
Anyway, all right. So step 1, we good on step 1 there. Step 2, I need to show that it's decreasing. Okay, so I'm going to consider the function of a sub n as a function of x. So I'm going to say f of x equals ln of x over x, and I'm going to take that derivative. Okay, and then in this case we have to do low d high, so it's going to be low d high minus high d low all over low, which reduces down to 1 minus ln of x over x squared. Now, okay, so what makes that 0? So what makes the top 0? If you set the top equal to 0, you get that 1 equals ln of x. And what makes ln of x 1? That is e. And what makes the bottom 0 is just 0. Okay, so there's 2 values to kind of check between. And 0 is already kind of my starting point anyway. And then we got e right here. If I plug anything in between, like, so e is 2 point something, so maybe I can plug in like 1. If I plug 1 into that, ln of 1 is 0, so it's positive on top, and positive on bottom, so that's positive. And anything past e, like 2, 3, 4, is going to make ln bigger than 1, so it's actually going to be negative for my interval. Okay. So, therefore, so ultimately it's decreasing, so therefore, by alternating series tests, I'm just going to write series converges. Okay. And if you want me to say what I did earlier, we can say it's decreasing whenever n is greater than or equal to 3 in this case, since e is like 2 point something. So I need to move on to the third term before it starts decreasing. But anyway, ultimately it's decreasing and we're good to go. What do you guys think? Alternating series test, not the worst thing in the world to do? So if you ever see that -1 to the n-1 power or n power, and they're asking about convergence or divergence, that's all you have to do.
Definitely feels a lot simpler than the last unit.
Yeah, the last unit, yeah, it's not too bad. So the other test we have for convergence and divergence is the p-series test. We also have the one for geometric series where you have to figure out the rate, and that's really about it. That's all we need to know right now. So, okay. All right, here's the deal. Any questions on any of this stuff before I move on? This is the most important stuff. Okay. Here's the deal. So the next 3 or 4 slides, is kind of the next piece of this unit. So this unit that we're in, 9B, it's all about trying to decide if a series converges or diverges, which we just did it for alternating series. Awesome. And then for each types of series, there's an additional piece that they want you to be able to do. They want you to be able to estimate the error involved in approximating the sum. Okay. Now, looking over all the stuff that we're keeping and all the stuff that they're cutting out, it looks like that there is, it looks like they took out completely all of the error stuff. Okay, so it looks like they kind of took out that piece of this unit. Now, for the sake of the video and just trying to give a little consistency, I'm going to continue with talking about error with alternating series. Okay, again, anything dealing with estimation and error with any of these tests I'm talking about, it is completely optional. But because it's a part of the same day, I'm going to continue ahead. So if you really just want to ignore me from here on out, that's fine. Because all you need to know is the convergence part. You didn't need to know this piece. But again, I'm going to spend a few minutes trying to go through it. Error is probably the hardest part, I think, but I think it's good to know. So are we good? Make sense? Any questions? Okay. And in the integral test, that day 1 that was optional, I went into what error was a lot more detail, but I can still give a pretty good explanation of it right now. So first off, it says if our series is -1 into the -1. So basically, if we have that alternating series piece, okay, and I had that, say I used B sub n instead of A sub n for some reason. But I said that is the sum of an alternating series that satisfies these 2 conditions. And all these 2 conditions is the alternating series test. Okay, they kind of reverse the orders here, but basically, if I have an alternating series that converges, okay, that converges to some sum, then this last line here discusses what the error is in approximating the sum. Okay, so I'm going to write out what each of these pieces mean. Okay, this literally means error. Okay, the R stands for remainder. Okay, the remainder is what's left over if I'm just taking the sum of a partial amount of the terms. What's left over is considered the error in the approximation. Okay, so the error is equal to literally taking the infinite sum, which is what S is, infinite sum, and subtracting S sub n is the partial sum. And they say absolute value because it can be plus or minus. You can be off in the positive or negative direction, okay? But do you agree that the error, if I'm taking a partial sum, the error in that partial sum is just the difference between what the actual infinite sum is and the partial sum, right? What's left over is kind of what I'm off by. Does that logic make sense? Any questions on that? All right. Now, that's the same with every single type of partial sum I ever find. But with every type of series, there is a way to approximate the error involved. In this particular case, okay, the error is less than or equal to b sub n plus 1. What that means is say I'm looking at an alternating series, okay, and I'm going to do the infinite sum, and I'm going to minus the sum of the first 5 terms. If I take the sum of the first 5 terms, I am off by no more than the value of the next term. Okay, the next slide is a really good visual that shows this. So I'll kind of show it in the next slide. Is there any questions on that before I move on? I'll give you a second to write it down. But error can be hard to visualize. That's my way to explain it. I mean, hard to visualize, I think.
Wait, can you explain the b sub n plus 1 again?
This part right here?
Yeah.
Okay, the next slide is going to do, I think, a better job explaining it, but I'll just say that if I'm taking the sum of, say, the first 5 terms, so something plus something minus something, that's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5. If I take that sum right there, then that is going to be off from what the actual sum is by no more than the value of the 6th term. So let's say the 6th term was equal to like 1/2. Then I'm saying that this sum that I just came up with, the error in that is no more than off by 1/2 of what the actual sum is. Here, let me show you why that is. This is the slide that shows it. Okay, it's kind of like you're used to seeing it looking like this. You're used to kind of seeing it look like this. Like this is your L, and these are your sums, and they're converging to some value, but they just kind of have it flipped upside down here on its side. Like right here, this value, okay, that is my infinite sum. Okay, so if this is an alternating series, the series is going to approach that sum. Okay, now here's the thing about what happens as I take the partial sums. Okay, the partial sums, if you look at a graph, we've graphed this multiple times. If you look at our graph, the sum is alternating between more than what it should be and less than what it should be. It's going back and forth and getting closer and closer to that value L. Okay, so let's look what happens. Okay, let's say for instance, okay, so here we're starting off with a sum of 0 because we haven't added anything. I'm going to add my first term. And if I add my first term, I'm going to be at this partial sum value here. If I add my next term, which is a negative value, it's going to take me to this sum here. So this is the sum of the first 2 terms. Let's for instance, let's look at an example. Let's look at the sum. Let's look at the sum of the first 3 terms. Okay, here's the sum of the first 3 terms. Notice how it's getting closer. So this sum is really close to what the actual value is. It's getting closer and closer. We call this the infinite sum, I guess the absolute value, the infinite sum of S minus S3, right? That is what my error is. That's what I'm off by. I'm off by this much, okay? Now, that value, if you notice, is less than or equal to the value of my next term. Do you see how this line is greater than this line right here? It's because the next term is going to take me to the sum of 4. It's going to be a bigger value than my remainder, so I'm on the other side of the limit. So this is actually less than or equal to a sub 4. Does that make sense? So the remainder, this line right here, the remainder is actually less than the value of my next term. That's that. If I add that sum, it's going to take me to S sub 4. Does that make a little bit of sense? Any questions on kind of the picture that I drew there? So that's the cool thing about alternating series, because the sum is always alternating on either side of the actual infinite sum, that that the error is always going to be less than or equal to the next term. Okay. So, yeah. Let's look at an example.
My phone just died, so.
Oh.
Not all the time.
Okay. This next example is kind of a. I really got 2 more examples. Okay. This next one's kind of the fun one. Okay. All right. This is how you would see it. It says, find the sum of the series correct to 3 decimal places. Okay. So like, it's not asking you to find the actual infinite sum. It wants you to find an approximation. It wants you to find an approximation that is off by only 3 but that is accurate to 3 decimal places. Okay. So this is how you would do it. The first thing is you got to identify, is it convergent? Okay. So we're going to do our test real quick. Test isn't too bad. Our test is saying, okay, so my A sub n, so the limit.
Your volume's out again.
How about right now?
It's fine now.
Good now.
Ah, okay. Is that good right there? Okay, cool. 1 over n factorial. Okay, if I take that limit, the bottom's getting really big, so yes, that is going to be equal to 0, so that's check. And number 2, for sake of time, I don't want to bore you through it all, but because, well, actually, we can't even take the derivative of n factorial. We would discuss it more this way. 1 over n plus 1 factorial is less than 1 over n, and that is true. We can't take the derivative to discuss it, but I can discuss it as the next term. Like the next term is always going to be bigger in the denominator than the previous term, so therefore, yes, it's always going to be decreasing. Okay, so therefore, convergent. And I don't want to spend too much time worrying about the convergent test for this one. Okay. Now that we know this convergent, we can approximate its infinite sum, and we want to approximate it within 3 decimal places. Okay. So how I'm going to do that is, I'm going to use that little formula we talked about. I'm going to say that the infinite sum, which is what I'm trying to approximate, minus some partial sum, we'll call it S sub n. I want that difference, okay? I want that error to be within 3 decimal places of the actual value. So like I want this to be less than or equal to 0.000 and then some number afterwards, okay? I want that difference to be less than or equal to 0.000. That will ensure if the difference is within that range, then that's going to mean that my partial sum is within 3 decimal places of the actual sum. Does that make sense? So the difference between the sum and the infinite sum, all right, or the infinite sum and the partial sum, I want it to be off by no more than 3 decimal places. Okay. All right. So we're going to have to figure out what term. I got to find the term in my series. I got to find the term in my series that the first term that gives me a value that is equivalent to this. Okay. So for instance, like, okay, so I'm trying to decide if I want to go through this whole thing with you or just go ahead and tell you. All right. You're going to have to figure out what the n value is. You're going to have to plug into this series until you find, into this sequence until you find a value that is within this range. So I did this in my calculator, okay? You can test points by plugging them in to this sequence if you want to, but I did it in my calc, okay? And I did it in the sequence menu. I did sequence, and I did, y equals, then I plugged in all this stuff. I went over this briefly with y'all in a previous lesson about how to plug this stuff in, Like I talked about U of N, you plug in the series. I talked about the other one you had to plug in was U in min, which is just your minimum value or minimum value term, I guess. Okay. And then we can go to second graph. Okay. And it's going to start off with like n equals 0, n equals 1. And we're going to go down the list. And if you go down that list, actually at n equals 7, n equals 7, the value is 0.0001984. Okay. And that is the first term in the list, okay, where the value is 0.000 some number. So that means at a sub n, or a sub 6, if I were to take the sum of the first 6 terms, that the error or the difference between that and the infinite sum is going to be less than or equal to this value here, ensuring that it's going to be correct to 3 decimal places. Does that kind of make a little bit of sense? So I'm going to write that out on the next slide here. I'll give you a second. Let me write that down, because I'm going to move on to another slide to keep writing. But I'm going to show you. Yeah, go ahead.
How do you calculate the infinite sum for that?
Oh, you can't. We're approximating the infinite sum.
Okay, so what do you put in the calculator?
Do what? Oh, you plug in a sub n, or you plug in the whole thing. Like you plug this in.
Oh, okay.
Don't plug in the summation part. Don't plug in the summation part. So this is where you plug in your series. And that's with the -1 included as well. So -1 to the n over n factorial. Okay. So you plug all that in, plug in your minimum value, and then go to your second graph. You can go down the list, and n equals 7 is the first term, all right, to where it's 0.000 number. Meaning, and I was going to start to write this on the next slide, but meaning that if I did s minus s sub 6, okay, that's going to be less than or equal to a sub 7, okay? And a sub 7 is a decimal. It's 0.0001. Oh, someone's calling me. I'll talk to her in a little bit. But, and that difference is within 3 decimal places, so that's pretty cool. Okay. All right, questions on that? All right, we're almost done. Hopefully that this will make a little bit more sense. Okay, so I'm gonna move on to the next slide. Okay, so what I wrote was is that s minus s6 is less than or equal to a 7. Okay, well, what is s6 equal to? What is the sum of my first 6 terms? And that's pretty simple. All you got to do is just plug that into your calculator. Go n equals, we started at 0, we went to n equals 6, and I'm gonna do -1 to the n over n factorial. Okay, if you plug that into your calculator, that's all I did. I just plugged that in the calculator to figure out what my sum of my 6th term is. I get, I'm gonna write the decimal here, 0.368055556. Okay, and I know that because of how I found my 7th term, I know that this partial sum is correct within the first 3 decimal places. Because if I took the infinite sum and subtracted this value, I'd be left, if I did s minus this value, I'd be left with no more, or it'd be less than or equal to 0.000 something, something, something. Okay, because I just found that. Okay. All right, well, how do we approximate the sum based off of that? Okay, well, I know that the absolute value of S minus, and we just found S6 to be 0.368 or 0.55556. I know that difference is less than or equal to 0.000198, the value of my 7th term. Okay. All right. Now remember how we solved we're solving for S basically. And remember how we solve inequalities is we get rid of the absolute value and we have it basically like this. So we're going to have S minus 0.368055556 is greater than or equal to negative 0.000198 and less than or equal to positive 0.000198. Okay, I know that difference is between those decimals. Okay, that's how absolute value works, remember. Now, if I want to approximate what my sum is, what my infinite sum is, I'm just going to add this value to both sides. Okay, I'm going to add 0.368055556 to both sides. And when I do that and simplify it, I know that my infinite sum is going to be between these two values, which I wrote down. If I add this to both sides, I get, on the left side, I get 0.367587149. And on this side, I get, I can't read it, 0.368253963. Okay. And now, so without finding my infinite sum, I have a really good idea of what the infinite sum is. I know that it's correct between these 3 decimal places. I know it's going to be about 0.368. And that's it. So the hardest thing, really, the most complex, like you had to find a sub 7. I think that was the hardest part, honestly. Trying to think about what value that next term was going to be. And then it's just setting up this formula and solving for S. That's all it is. Does that make a little bit of sense? Any questions on that? I'll give you a second to write that down. And the next slide goes by a lot quicker. All right, last one and I'll shut up. This one's easier. All right, I'm already telling you it converges, so we don't got to do the test for convergent. And all I'm asking you to do is just to estimate the error between the sum of the series and its 15th partial sum. That's it. The 15th partial sum. I want to know what that error is going to be. Okay. So all you have to do is set up our little formula. Well, I know that the error is going to be equivalent to this. I know that the error, which is S minus S sub 15, the 15th term. I want to know what that error is. Well, I know that error is going to be less than or equal to the next term, which is A sub 16. All I have to do is find those values, and that's it. Okay. So, like for instance, like S sub 15 is equal to, we'll plug in 15 in. So the summation n equals 1 to 15 of negative 1 to the n. Oh my God, that's ugly. Negative 1 to the n over square root of n plus 1. If I did that, I got, what did I get? I got 0.379, 531, 3791. And if I found A sub 16, That's just plugging it into, so it's -1 to the 16th over the square root of 16 plus 1. And honestly, I think we can do that in our heads. That's +1 on top. And isn't that just going to be 4 plus 1 is 5 on bottom? So I know, it says to estimate the error. I know 1/5, what's that point? Is that well,
2,
right? I know that my error, if I do the sum of the first 15 terms, I know that my error is going to be within 0.2 of the actual sum. That's all that means. So you can write that out if you want. You can say the sum minus that 15th sum, which was 0.37953133791. I know that that partial sum, if I take the difference from the actual sum, is going to be less than or equal to 0.2. I know that that's how far off I am. So that's the error. I just estimated the error. The error is going to be plus or minus 0.2. And then if I asked a follow-up question, I said, well, estimate what the sum's going to be, then I'm just going to do what I did before. I'm going to say S minus 0.37953133791. I know that that difference is going to be between -0.2 and +0.2. And if I add this to both sides, my final answer is just plus or minus 0.2 from that, which I got to be let me see here. I did not write it down. Dang it. Yeah. Okay, I did not write it down. Oh well. Okay, well you can do it in your head, right? That's not right. Isn't that just going to be 0.57953133791? And if I subtract it, wouldn't that be crap? Negative 0.5795313. I don't know. But anyway, you can check that.
No.
Nope,
Would you like -2 plus 0.3795?
Oh yeah, -0.2 plus it. Yeah, you're right. I'm an idiot. So that'll be 0.1, right? Is that right? Negative point.
I got 0.579 ...
For the right side or the left side?
Left side.
Did I do the right side wrong then?
Well, because isn't it negative?
It's -0.2 plus 0.3, so that should be positive 0.179, right? Like -0.2 plus 0.3, isn't that positive 0.1?
Yeah, sorry, I did positive. I didn't do negative.
Okay. You're fine. Okay, so there we go. That's the final. That my sum is somewhere between those two numbers. It's off by 0.2. And that's it. I mean, I wish I could have done integral tests with y'all first because that really describes error a lot better. But hopefully it made a little bit of sense. Again, error is not going to be tested. So if you didn't like it, that's good. The biggest thing is that we understood what alternating series test for convergence and divergence is. Okay. So, any questions, comments, concerns, anything you want to say? Before you do, I guess I'm going to say, okay, bye. I'm not going to record anymore. So I'm going to say stop recording. Yeah.